Uključili na današnje predavanje koje će biti o armirano-betonskim zidovima, odnosno nekim seizmičkim aspektima tih konstrukcija. Molio bih sve da isključe mikrofone za svaki slučaj. Predavači nam dolaze iz Belgije, dr. Hoult i dr. João Almeida, koji su se u karijeri između ostalog bavili i armirano-betonskim zidovima. Današnja prezentacija temelji na pre svega njihovim rezultatima eksperimentalnih ispitivanja, a uz neku moju molbu će se jedan deo posvetiti praktičnim problemima. Ryan and João, the floor is yours, so
okay.
You wish.
Thanks, Vladimir. Let me share the screen, hopefully the right one. I guess can you see my screen?
It's not the presentation view though.
Okay, wait a second.
Perfect.
That's the one. Yep.
Okay, let me just pull you here to another screen. All right. And okay, so it's good for everybody, right? Yeah. So okay, so hello, so good afternoon to everyone in Serbia. So first, also a quick thank you to Professor Božidar Stojadinović and Professor Vladimir Vukobratović for their invitation for us, for me and Ryan to give you this seminar. The Serbian Association of Earthquake Engineering, you seem to be very dynamic. So I was just discussing a few minutes ago. So it's a very good example for other equivalent associations in Europe. So we were asked to do a presentation that would be rather practical. So we believe that the majority of the audience is from practice, from the industry. So that's what we tried to do. So we greatly simplified all the technicalities. So we will just mainly present some of the main findings from, let's say, a decade long of experience on experimental research of reinforced concrete walls. Okay, so we will try to do, let's say, the best of these, say, around 50 minutes or so. Okay, so why reinforced concrete walls? So I guess, as I'm sure you all know, so reinforced concrete walls are likely, let's say, the most effective lateral load resisting system for earthquakes, of course, also for wind actions in tall buildings, more flexible buildings, or more flexible structures, and they tend to perform very well during earthquakes. So that's not always the case. First, here is a picture from Christchurch after the earthquakes of 2011, and so it is, of course, it is important to improve the understanding of this type of members. So in Serbia, as far as I could understand, yesterday I did just a very quick research on reinforced, on your type of building stock typologies, and if I understand well, reinforced concrete is the, let's say, basically the backbone of your modern building stock. If this is correct, I mean, you had a very rapid urbanization from the 60s, 70s, 80s up to the 90s. If I understand well, this was mainly using, say prefabricated RC panels, Soviet style. And then also some interesting, some brutalist architecture, which is actually something that we also have here in Belgium, namely in Louvain-la-Neuve, where our university is located. But so it seems like after the 90s, the pace of construction reduced a little bit. I don't know if how things stand now in Serbia, but I am pretty certain that reinforced concrete is your main type of construction. And so basically all medium and high-rise buildings, I guess in Serbia, they are made with reinforced concrete, and most of them will have walls. So walls are members that also here in this the other bridge. I have never been to Belgrade, but walls you can also see them in. First, you can see them in as a bridge pier. So basically, any additional understanding that you can get from the behavior of these members will help you. So I was also not familiar with seismic hazard in Serbia. I can see that Belgrade and apparently some of the other two bigger cities, they are mainly on a low seismicity regions, but I guess, I mean, all of your design or assessment of existing buildings in these more moderate to high seismicity, it would be interesting for you to know a little bit more about walls. So we will basically share you, give you an overview of our experimental work on different aspects. So we were doing a research, so we more or less, we always need to do something that is relatively specific. So we will not share, of course, all the details. We will skip, of course, all the numerical part. We will basically give you, present the main findings and some key takeaways. So the first topic is global out-of-plane instability. So this corresponds to some of my first experimental research when I was still in Switzerland at TPFL. And this global out-of-plane instability corresponds to maybe a less known deformation and failure mode for you. So you certainly all deal with shear failures and flexural failures, more brittle, more ductile, maybe sliding shear. That Boz also has worked quite a bit. Global out-of-plane instability is maybe less familiar to you. I should also say less familiar to see it in, say, earthquake-affected regions. So basically, just to give you a quick overview of how does this mechanism develop. So if you just consider here a wall under, say, let's say, seismic action in this simple representation, you will eventually have some flexural cracks that form at the end regions of the walls. These will cause some tensile demands in the rebars within the cracks. These demands, if sufficiently high, they will, of course, they will cause the reinforcement to yield. And then during unloading, if the cracks, or let's say while the cracks, they remain open, you have all the compression force basically being resisted by these two rebars. Okay, if there are two layers of reinforcement. If the cracks, so in compression, if the cracks do not close, it may even happen that the reinforcement near the let's say the concave side, the intradose of the wall, may also yield in compression. At which point the out of plane stability is greatly compromised. There will be then high developments of out of plane bending moments and an increase eventually of displacements. At this point, there are basically two scenarios that can occur. So basically either the cracks on the intradose will close and basically some stiffness will be regained and the displacement, or let's say the verticality of the wall is restored. Or if that is not the case, so basically if the second reinforcement layer yields before the crack closes, then, well, theoretically at least, out of planes can increase and possibly lead to a buckling failure. So this was basically just a quick context. This was something that research that started because around 2010 in some countries in South America, say namely Colombia, they really started having massive amount of construction with these very thin walls. I mean, when I say thin, they were like 10 centimeters, sometimes 8 centimeters, with just one layer of reinforcement. And besides this, with also low ductility meshes. And so basically, it was in this context that we started studying these deformation and failure mode, and we tested it through wall tests and boundary element tests. So for instance, here just very quickly an example of a wall that we have tested. So if you plot, so this is a loading, I mean, there is also vertical loading, bending moments applied, but if you just look at the hysteretic response in terms of force displacement, you maybe would not see anything particularly specific to this response. However, if you look at the out-of-plane displacement, and now I'm just going to quickly play this video, or actually it's more kind of a time lapse, let's say, when we'll be loading the wall from the right all the way to the left. So I'm going to click it, and you will see that the wall starts displacing out of plane, and then the cracks closes, it straightens up, and eventually the wall will fail. Okay, so basically, in a simple way, we could see that there was some influence of these out of plane deformations to the failure of the wall. But very interesting as well is an information that you can see in this graph that plots the out of plane displacement. Okay, it's just normalized with respect with the thickness of the wall versus the in plane displacement. And what you can see is that actually the maximum out of plane displacement occurs for approximately drifts that are very close to zero. So the maximum out of plane displacement does not occur when, let's say, the boundary region is in maximum compression. Okay, so this is, let's say, one finding that may be, let's say, interesting for overall for your general knowledge on the behavior of walls. We tested also a second wall where we imposed simultaneously out of plane displacements here at the heads of the wall. We could see that also caused some decrease in the displacement capacity of the walls. I don't really have much time, and for other reasons I will skip this. We basically still within this topic, there was a second experimental campaign that we have done, and this test campaign was on boundary elements. So these boundary elements, again, I don't know how familiar you are with experimental programs, but basically these boundary elements are tested under tension and compression, and they basically, the idea is that for a flexurally responding wall, they work as proxies of the behavior of the wall. Okay, and the idea is that, well, you have a simpler loading, so just uniaxial loading. The test specimens are also cheaper, and so basically this is a technique that researchers use mainly when we try to analyze the effect of several parameters. Okay, so this is what we have done. So we went on to carry out boundary element tests of 12 units with a single layer of reinforcement, so very highly monitored, and basically, so we imposed just a top displacement. Well, actually, it was top, but it was at the base of the specimen with a certain loading protocol, increasing this displacement, and we basically went to verify or to analyze the effect of several variables, namely the thickness of this element, the number of bars and their diameter, and the percentage of the reinforcement content. And finally, also, let's say, this eccentricity of the position of this single layer of reinforcement. So again, I will not go through the whole details, but just to maybe share another. So let's say the critical aspect of the behavior that can trigger this out-of-plane instability. So when you plot for each of these specimens the imposed, let's say, top displacement and the maximum out-of-plane displacement, what we see is that while this strain demand, so the maximum tensile strain demand, remains limited, the out-of-plane displacement is relatively small. Once it increases significantly, then the out-of-plane displacement starts increasing until eventually it reaches failure. So this is something that you could keep in mind, that, well, of course, it's the maximum tensile strain demand that will be a signal of how vulnerable these walls are to out-of-plane instability. And the more reinforced you have this boundary element, the more prone they are to this instability mode. Now, this was a very extensive study. I will not share more details, because I believe in Serbia you mainly, I don't know, but I believe that you mainly build with 2 layers of reinforcement. And so a summary of my experience with many also analytical numerical studies is that if you are building with 2 layers of reinforcement and you respect, say, the minimum thickness prescribed in, say, modern codes, in the Euro code, for instance, or the previous codes that you are using, the out of plane, so the global out of plane buckling, not local out of plane, but global out of plane buckling will not be generally a concern. Okay, so this is maybe another message that I would like to share with you. Now, a second topic that I will try to address a little bit more in detail, I mean, still taking into account the time that we have, has to do with, but maybe a little bit more interesting to you, because ultimately all walls will have lap splices, has to do exactly with the behavior of these lap splicing. And for instance, you see here is the foundation of a school in Turkey, just before the big earthquake of 2023 has hit. And actually, many reconnaissance missions showed that there, let's say, many of the poor behavior of wall buildings in Turkey was partially connected with the fact that they were using these poorly confined and short lap splice lengths. So I guess, of course, that Serbian, let's say, design and construction reality is very different than the Turkish one. But, well, as I said, lap splices exist. And so it's something that may be interesting for you as well to understand a little bit how the effect of this, say, design detail. So here we also tested for this topic. We also conducted tests in walls and also in boundary elements. So basically in walls, again, it's a very, very simple story that I'm telling you, but basically here what you can see in comparing here the response, the cyclic response of a wall without lap splices in blue and with lap splices in red, is that the presence of lap splices here just over these this short lap splice length actually can very significantly reduce the displacement capacity of the walls. Now, at the start of the research, so this was already maybe 9 years ago, this is basically what we knew from different contributions of different researchers, is that well-detailed lap splices, if they are in the plastic hinge region, what they will essentially do is that you have the double of the reinforcement, and this will basically force the relocation of the plastic hinge length above this region, which is not ideal because you can have, say, increased shear demands. But well, so we knew this. We also knew, so from several wall tests, that short and unconfined lap splices will possibly mean that the wall will fail even before you reach the flexural strength. So it can somehow fail somewhere here, let's say, without reaching the capacity in flexure. Whereas, let's say, a medium length and with medium confinement, then you can have a little bit, as I have showed, a reduction on the displacement capacity. And we knew, although not very much in detail, that some of the parameters that were influencing the displacement capacity were the lap splice length, the confining reinforcement, the kind of a moment gradient, let's say, the shear span ratio, and the loading history. And so we basically, using the same concept as before, we decided to investigate, again, using these boundary elements, as I mentioned, which is what we can use when you have many tests to do, to analyze the influence of each of these variables. And so basically these spliced RC elements, they are, let's say, supposed to be representative here of these boundary elements that are mainly subjected to tension and compression. So we tested 24 units, so 22 with lap splices and 2 here in green with continuous reinforcement as kind of as a reference, with different lap splice lengths, so very short to pretty long lap splice lengths, confinement reinforcement changing also from 0 to 0.3, and different loading histories from monotonic to different types of cyclic loading histories. The test setup was actually very similar, as I showed you before. The main cyclic loading protocol, which we called C1, so it's very classical, but basically it had, just a little call your attention to the fact that it has a ratio tension compression of 10:1. I'll come back to this later on, okay? And so what did we get? So we had the wall instrumented, the boundary elements instrumented they had this. Very sorry. The for the bottom chassis, the lap splice strain capacity was much higher. So again, so at the end of this work, we derived some predictive equations for the strain capacity of the lap splices that basically had that have this mutual influence between these parameters, namely the lap splice length and the confinement reinforcement with these two basically zones that I have mentioned before. Okay, so this is just something again that if in your practice as engineer you come across, maybe it could be useful. Yeah, so this was basically the first two topics. Now I will pass the screen to you, Ryan, so that you keep on giving this little overview.
Sure thing. I think you might have to stop sharing your screen.
Stop sharing?
Okay. Yep. There we go. Okay. Can you see my screen?
Yes.
Perfect. Okay. So, first of all, again, I echo what João said. Thank you all for giving us this opportunity to present to you. So I will very quickly talk about some of our work on residual displacements. And then I'll very briefly talk about some of the torsional research that we've done recently on walls as well. So I always like to start off by talking about the Christchurch, New Zealand case study for residual displacements, because it was such a profound earthquake in a way in terms of of what happened to the actual city itself. It was only a magnitude 6.2 earthquake, but it essentially ruptured right underneath the city itself. Even so, even with those large earthquake demands, there was, let's say, a very limited amount of deaths, fortunately, with most structures, let's say, performing pretty satisfactory, particularly from the point of view of an engineer. And we really put this down to the fact that in the 1980s, the capacity design was really introduced, which really helped the design of reinforced concrete structures. And it was also linked to this performance objective of life safety as well. So where you had effectively allowing your occupants of the building to evacuate the building. So you really wanted your building to be still standing. Hopefully my internet is, I'm having some messages that my internet is not great. So hopefully it's all good still. Okay. So even though there was, let's say, limited damage, it still cost the economy in New Zealand about 20% of their GDP. So that's $40 billion worth of damage. And it wasn't necessarily because of the let's say, the collapsed buildings itself. It was mainly because there was, let's say, roughly 25% of the buildings that were no longer vertical. So that is, they had some sort of tilting to them. And this is when residual displacements become reasonably important, because they're essentially a measure of how much they're tilting, how much damage there actually is. To give you some more emphasis on this, 60% of the reinforced concrete buildings were demolished, considered uneconomic to repair. And that is simply because of those tilts. It wasn't because they were actually collapsed. And so I guess there is a sort of almost design shift recently in the, let's say, the last decade or two, to really concentrate more on low damage technologies for large earthquake events, rather than this life safety performance objective. And of course, we have the capacity to do that with things like base isolation, but they can be very expensive. They can be very complicated to incorporate into your design. And so one of the things that João and I have been really investigating is how can we implement low damage technologies in a really simplistic way. When I refer to residual displacements, one of the things, one of the ways that we can really derive that, if you think of a quasi-static reverse cyclic test like this, so this is just looking at the force displacement plot. We look at the displacement the wall is pushed, and then on returning back towards its center position, we look at the displacement, we look at the displacement that it basically tries to return to at a force of 0. So that is essentially the residual displacement corresponding to that in-plane drift. So one of the ways that we, I guess, are coming up with some ideas on how we can implement low damage technologies in a, let's say, cost-effective way, in a rather simplistic way to implement in construction, is just by substituting the reinforcing steel bars. So João tested these walls a few years ago. One of the walls was reinforced with conventional steel. The other one here, if I just get maybe my highlighter out, was reinforced with what's called shape memory alloys and over a really small length at the base. These shape memory alloys, I'll explain a little bit more in the next slide, but they can be very expensive. They're about $500 per meter. But the idea is not to have the shape memory alloys extend throughout the entire structure or throughout the entire wall, but to have them over a very short length at the base in the plastic hinge zone. So to give you a very quick summary of what shape memory alloys are, they're essentially special metals that can remember their original shape. So when you bend or when you stretch them, they can essentially return to their original shape, either through superelasticity or when they're heated through this so-called shape memory effect. So anyway, this is what makes it really useful in concrete structures, because they can absorb the energy during the earthquakes and they can recover and effectively reduce the damage. This superelastic effect is only possible because of the material essentially deforms in the martensite stage. So this is over here, and that's under the stress that it's been imposed. And it's able to essentially return to its austenite stage after the stress is released. So that's a very quick summary of what shape memory alloys are. Okay, so this is a force displacement plot of the two walls. So in the gray, you have the reinforced concrete wall reinforced with steel. And in the black line, you have the force displacement plot of the shape memory alloy. So again, the shape memory alloy is only over a really small length at the base. So what you can see, of course, from these plots is they're very similar in terms of their force displacement behavior. But what we're interested in is if the residual displacements were reduced by introducing that shape memory alloy. And the way we can do that is by looking at each one of these peaks in terms of the drift that was imposed on them, and then looking at how the residual displacement on returning to a force of 0 is reached. And so we can plot that, right? So we have two relationships here. I'll get my highlighter out again. This is the relationship here in gray for the steel reinforced concrete wall, and then here in the highlighted blue line is the reinforced concrete wall reinforced with shape memory alloy at the base. And if we assume, for example, that you have a limiting drift of 0.5%, after which it's, let's say, uneconomic to actually repair the structure and you have to demolish, well, you can see that for the steel reinforced wall, you're reaching that at about 1% drift. But if you introduce a very small length of the nickel titanium shape memory alloy, you can see that you're almost getting double the in-plane drift there. And so this is a very quick overview of some of the work that we've done with shape memory alloys. We think that it's got some potential for reinforced concrete structures. It is still expensive, but we are currently investigating things like iron-based shape memory alloys, which are about a fifth of the cost. And we're also investigating other materials such as the GFRP reinforcement as well, which I think João will talk about very briefly at the end of the presentation. I wanted to maybe change gears here now and just talk about another sort of research focus of ours with reinforced concrete walls, and that is torsion. So the first thing to mention is with buildings that are subjected to earthquakes, torsion is sort of inevitable. The amount of twisting or the magnitude is really dependent on a lot of factors. But the building that you see here on the screen sort of represents, let's say, a worst case scenario where you have the center of mass somewhere towards the center of the structure. You have the center of the stiffness out towards the primary core in the perimeter. And of course, the earthquake ground motions are going to essentially provide that earthquake force through the center of mass. but your inertial response will really come through the center of stiffness. And it's this eccentricity distance and this sort of force couple that's generated, which really makes this sort of building twist. And then, of course, this core will really have to do most of the work in terms of resisting those torsional actions. Even just stating all of that, there is really a limited amount of research that has been performed on walls for torsion. And so we decided in 2022, we would instigate an experimental program where we would subject a wall to torsion. So this is the U-shaped core wall, if I raise all the text. So this is the U-shaped wall cross-section that we tested with the reinforcement detailing. These were very standard sort of quasi-static reverse cyclic tests. The first wall we actually tested in flexure, so we just bent it back and forwards essentially. But the second wall we rotated about its vertical axis in torsion. And it's this wall that I want to primarily focus on over the next couple of slides. So hopefully my bandwidth isn't too bad to show this video. Okay, I'm getting João's reaction there, so maybe it's not too good. But I will play this video anyway. It's a time-lapse video of the wall rotating back and forwards. And what you'll see in a moment is the wall panel in front of you essentially will start to fail, and it will fail towards the boundary end, and it kind of rips open more or less once it reaches really large rotations. You'll also notice the amount or the heavy amount of instrumentation that we used to monitor the wall and to collect data. This was really important for us because, as I mentioned, there really is a lack of information on how these walls perform in torsion. And so it was really important that we collected a lot of data so that we can then validate numerical models and then analytical models as well. Okay, so once we collected that data, we then moved on to thinking, well, how can we essentially try to predict or simulate the torque and the rotation of these walls in a very quick and easy way? And so one of the things that we wanted to investigate was what is the interaction between the bending moment and the torque. And one of the primary things that we wanted to see was there a reduction in the bending moment capacity when you introduced that torque into the system? And so we adopted a very simple analytical model that was done in 1981. It was originally done for beams, but we modified it for cantilever walls with axial loads and all of these other things with confinement and things like this. I obviously don't have a lot of time to go into the heavy details of the analytical model, but this is just really to show you that the analytical model did a really good representation and simulation of what the torque rotation response was in comparison to, let's say, the quasi-static test that I just showed you previously. So what we wanted to do was take this analytical model, which was for torsion, and we wanted to combine it with a sectional analysis, also called a moment curvature analysis, so that we could see what was the performance of the wall for different torque and moment ratios. So this plot here is giving you the warping moment of the wall at the base with torsion as a function of the ultimate moment of the wall. You'll see a few data points there. You'll also see a few lines representing different wall heights. The thing is, the bending moment, very similar to the warping moment, is independent, of course, of the height of the wall. So that's really not a problem for this. And we also have two positions. So if I just quickly maybe draw the wall, if this is the U-shaped wall, we have position C, which is actually pushing the wall towards this direction, and position D, which is pushing the wall in that direction. Each one of these data points is for a different torque to moment ratio. So for example, this data point down here is for a torque to moment ratio of 0 to 1. So that is pure bending. And conversely, up here, you have a torque to moment ratio of 1 to 0. So that's pure torque, or pure torsion, I should say. These data points here, for example, are for different torque to moment ratios. I think one of them, for example, is a 1:5 when you introduce that in. And so you can clearly see, I hope you can see from this figure, that as you introduce torque into the system, your bending moment or ultimate bending moment of the wall is actually reduced. So that's not the only thing that we want to see. We obviously want to calculate our torque as well in the wall, our ultimate torque in the system. That can actually be calculated fairly easily through this function here. So you take the warping moment and you divide it by this function C. The parameter C is actually just a height. This equation is actually very similar to how you would easily calculate, for example, your base shear if you had the ultimate moment of the wall. You just divide it by the effective height of the building. This, of course, has some built-in assumptions to it. I'm just simplifying it down for this presentation, but for the sake of argument, this value C represents sort of almost like an effective height where you apply a concentrated torque to get that ultimate warping moment at the base of the wall. So just following that logic, we can then calculate what the torque is in the wall. And this plot is the torque with the moment of the wall. The torque is normalized to the ultimate torque under pure torsion, and these moments have been normalized to the ultimate moment of the wall under pure bending. And I think you'll be able to see that there is some sort of shape that takes from this interaction diagram. And we've suggested that you can estimate this sort of interaction with a very bilinear sort of response. So the reason why we did this is because in all international building standards and codes, you cannot design a non-planar reinforced concrete wall for torsion. It's just not possible. All of the guidelines for torsion in these building codes are related to circulatory torsion or pure torsion. And of course, these non-rectangular sections are governed by warping instead. And so we wanted to start trying to think about, well, how can we actually try to let's say maybe revise building codes in the future and start thinking about how engineers can actually design for these things. But what we also thought is this analytical modeling approach is actually a little bit complicated, and we don't expect that everyday engineers to actually use this. So we actually wanted to think about, well, how can we, let's say, provide really simple design calculations to estimate what the ultimate torque of the walls are that engineers can actually use. So the first thing that we thought of is we looked at how these walls bend and what those sort of strain profiles would look like. So for example, the wall on the left is just a wall that's bending with this web at the back in tension. So the strains here, the pink strains, let's say, are tension, and the blue strains are compression. And conversely, on the right-hand side, you have the web of the wall here bending in compression. Okay, so if I just delete maybe this highlighter, so if we actually cut these sections in half and then we combine these two sections, what you end up getting is some sort of strain distribution that looks like this. And we realize that this strain distribution, which I've redrawn here a little bit better, looks very similar to the strain distribution that you get when you provide that torque to the wall and it's governed by warping at the base of the wall. And so we thought that if we can calculate the bending moment of the wall using these principles here, it might be possible to actually estimate the warping moment of the wall. And then, of course, we can estimate the torque from there. So I'm not going to go too heavily into calculations too much, although I do have a few equations on the next few slides, so I apologize if it's a little bit too heavy. But basically, we came up with this warping moment equation, which we think you should be able to readily calculate using, let's say, the software or the principles that you already know from just a normal wall design with bending moments. So to give you a very quick example, these parameters here that I've highlighted, they're really just dependent on the wall cross-section. So the paper that we've written with all of these equations, we've provided the equations for these two parameters in the appendix. And what you'll see is they're really dependent on things like the wall length or the wall thickness or the second moment of area, things that engineers obviously can really calculate, I think, pretty readily. The other thing here is this equivalent moment, the MEQ, is just something that you should be able to essentially calculate from a sectional analysis. So if you can readily calculate those things, you can then readily calculate the torque or the ultimate torque of the wall. I wanted to very quickly show you how you could put this into design practice, although I know I'm running out of time, so I might just very quickly move through this. But this was to give you a very quick example of if you had a case study building like this, you could easily calculate what the base shear was, the expected base shear from, let's say, a 500-year return period earthquake. I just used, I think, the Euro codes to calculate this. You would then be able to calculate what your design moment is just by multiplying it by the effective height of the structure. And then you could calculate, for example, the design torque if, for example, in this, let's say, rare case maybe, where you had the center of mass away from the center of stiffness, you would know your eccentricity. So it's assuming that this base shear is multiplied by that eccentricity distance to calculate your design torque. So this was important because it gives you your torque to moment ratio, which will be used for your interaction diagram on the next slide. This is indicating, for example, that you've got a bending moment that's about 2.5 times larger than the torque that's introduced in the system, but it's quite a substantial amount of torque in the system. So what we want to see is that ultimate bending moment of the wall significantly reduced because of the torque. So very quickly on how you could do this, the first thing is you want to do a sectional analysis. So work out what the ultimate bending moment of the wall is with the web of the wall here in compression. So you bend it in one direction. The moment of the wall web in compression is this. Then you want to bend it the other way, sectional analysis, and you get another bending moment with the web of the wall here in tension. If you take the average of those two values, this is your equivalent moment that will feed into the equation for warping moment. And those two parameters that I explained on the previous slide that are simply based on your section size. So again, things like wall length, your wall thickness, and second moment of area, for example. You can then very quickly calculate what your warping moment is. And then, of course, you can then calculate what your torque is just by calculating this equation here. So your warping moment divided by your value C. I don't think I'm going to have enough time, unfortunately, to talk about where this equation comes from. It's a closed form solution. It's essentially just based on the height of the wall and this characteristic length, also known as the torsional bending constant. I'll just quickly go through this to say that you can readily calculate the value of C and then, of course, readily calculate what the torque of, or what the ultimate torque of the wall is. This gives you essentially the interaction diagram because you know what the ultimate torque of the wall is, you know what the ultimate bending moment of the wall is, and then of course you can join these two lines using, again, some very simplistic equations that we provide in the paper. And the cool thing here is you can really just plot your design moment and design torque, and you'll see that it's actually outside or inside this interaction diagram. So the last thing that I really just want to point out here is when you have that torque introduced into the system, you really can have a really large reduction of your bending moment capacity. So for example, this is your bending moment capacity without torsion, but here is the reduction of your bending moment because of that torsion that's introduced into the system. So we're trying to think of ways that we can hopefully in the future provide some revisions to building codes to finally give the tools to design engineers to actually develop and design these walls for torsion. I'm sorry that was very quick, and I hope my bandwidth was maybe a little bit stable, but I'll hand it back over to João to maybe finish off the presentation now. So, I will stop sharing.
Thanks, Ryan.
How do I stop sharing? Stop share. Okay.
Perfect. Thanks, Ryan. Yeah, so you added some additional complexity to the presentation by we have to guess 20%, 30% of your words. Anyway, let me just is it okay? So basically. I hope you're seeing my screen. So basically, just quickly to wrap up, basically this quick overview of the experimental work that we have been doing over the last 10 years. So I'll just show you what we have been doing now. So Ryan has already mentioned a little bit some of the work that we have done with shape memory alloys. He did not show you. We also recently had a large shake table test with 2 walls with a 40-ton walls in Lisbon, U-shaped walls. We did not have the time to show you these results. One of those walls was classically reinforced with steel, the other with iron-based shape memory alloys. However, so this is kind of what we are now have been exploring. So alternative reinforcement materials to walls, and more recently we have been focusing on analyzing this GFRP, which stands for glass fiber reinforced polymers, that has been attracting a lot of attention from some designers and in industry, namely due to durability reasons, because this is a product that they don't corrode. So these bars are also going to be regulated for the first time in the next generation of Eurocode 2. I think it's NXR, if I'm not mistaken, which has already been approved, and for which there is very little response worldwide, I would say, in terms of the seismic response, because these are materials that are essentially elastically responding, and for which there is no ductility. So they are very strong, maybe 1,000, 1,100, 1,200 megapascal of strength. And they are always continuing, undergoing, say, continuous technological development. So we have done very quickly several tests over the last year and a half on, for instance, the bond strength. As you see, that there is a huge variability, and continuous progress. The bond strength is highly variable, so there is here a lot of room still to explore. So we are also using in our experimental tests more and more advanced instrumentation, namely distributed optical fiber sensors that we glue along those rebars, and that allow us to understand the evolution of the profiles of strains along the rebars, and that gives us very interesting information. Let's say also for recently we concluded a campaign where we basically managed to test here the band capacity of a rebar. So basically there is a part of the rebar that is unbonded. So we have here 30 tests that we have performed, and this gives us a little bit idea of how much the band actually how much strength it takes. I mean, with respect to the tensile strength, and we see that it is highly affected by this radius or the ratio between the bending radius and the diameter. So our specimens were here towards the low side, the blue ones, because it's a new resin which is fully recyclable, and also it's a thermoplastic, so it allows now to these bars to be bent directly in the construction site. But of course, the idea of those preliminary tests is to move towards the understanding of how these materials would behave, these GFRPs, if they are applied within a wall. Okay, so now we have finished the construction of a cage, of a GFRP cage. I don't know if I can see show here the video. So this is a little video just to show how actually flexible these rebars are, and yeah, so basically the tests will be, we have finished, this is a photo actually from yesterday, the rebar, so the cage has been, the formwork is completed, we'll test it next week, and in 1 month we will be testing this wall with more or less this type of test setup. Okay, so I mean, of course, we have many references that we can. For this was a very quick overview, and we are very happy to share this was like quite superficial in a way, but we are very happy to share more details if you are interested. And yeah, so we have here our contacts, and yes, of course, I mean, we I guess also welcome feedback from you, namely regarding, let's say, the challenges that you are facing in practice. I mean, maybe for possible inspiration for our future experimental research for the next 10 years. So again, I'm sorry for we think we overpassed a little bit the 50 minutes, but hopefully you can take something useful out of this out of our presentation, and so we're happy to try to answer some questions you may have.
Thanks, João and Ryan, for an interesting presentation, which I really enjoyed, and so many useful information in such a short time. It's a pity that we didn't make it like in 2 hours, you know. But maybe that gives us the opportunity to host you once again. So I'm opening the discussion right now. Anyone from the audience can ask a question. So please do. It's always like this. So I'm the one who starts the discussion. So I would refer firstly to the splices. It would be, even though I'm not so into the finance stuff, I'm not sure I even understand it, but the investors are pretty much into it. So it would be good to see the cost analysis at some point, because you have a lot of specimens and things which you actually tested, to see what's the difference in price in, let's say, like in regular splicing or in some mechanical devices, because they ask, let's say we give them some advices to switch to some mechanical devices, but they tend to keep with the approach, and you cannot explain to them that this is not healthier, even though it's cheaper, but it's not so cheaper, you know. So maybe you can put a comment on that one.
Yeah. So I mean, yeah. Yeah, you're absolutely right. I mean, so there is a lot of mechanical couplings that could eventually replace lab splicing. I have to say that I'm a little bit far removed to what is currently being done in practice, especially on say seismic regions in Europe. I think that in Portugal, which I know a little better, and in Italy, I think the same. I mean, I have the impression that the same difficulty in adopting even, say, minor changes in construction is always a big problem, and actually this has been something that we have always been trying to keep a little bit in our mind in the research, for instance, the experimental research that we have been doing. How can we, with minimal changes in the construction practice that seem to be so anchored for dozens of years, how can just keeping what they already know, how can a small change eventually be reflected on a improvement in the seismic response? And that's why, for instance, we explored a little bit the shape memory alloys, right? That could be like the construction, the companies can keep the know-how and just basically replace one bar by the other. And but you are absolutely right. I don't know where this resistance comes from. As you say, possibly even it would be in terms of, let's say, cost analysis, it would be preferable. But Vladimir, I really don't have any amazing answers to this.
Something to think about. And the next question is basically related to the end of the presentation. You've shown us some new rebars, which probably will be used in the future. So how do you see the in reality their application in combination with these new types of concrete, because they tend to produce concrete now with waste, with ashes, with things. And I'd be honest, I'm a classical guy, you know. So I understand that they can achieve the compression strength, which is good, but the modulus of elasticity is not so good in the concrete. So if you pair such a concrete with these new bars, what can we expect in reality? Have you thought about it?
Yeah, I mean, so again, look, sometimes I also lack the overall picture, in the sense that I know these rebars, they started being developed, I think, already back in the 90s in Japan and in other places. Then it picked up considerably in Canada and in the US, and now they are finally getting into Europe. So I don't believe that they will replace, at least for the foreseeable future, steel as a reinforcing material. That's not going to happen. They will, I do believe, however, that they will replace steel in many structures that will be in more aggressive environments, namely close to the shore, say the bridge piers, marine structures, and also in some specific applications where, for instance, where magnetic aspects can be of relevance in, say, in hospitals, or maybe in low-rise buildings, low-rise construction. Then that can be something that eventually will play a role. And so basically our contribution is mainly because our research on seismic, so the seismic response of these structures is really to try to understand until where they can go. So they will never be used in a highly seismic region. That is out of the question. But, well, there will be limits, right? The low, moderate. So this is a little bit until where we go, and to see if we can still somehow explore some ductility, or there is not really a ductility in the material, but through some concrete confinements and some let's say even cross-sectional shapes that are a little bit more conducive to having more ductility, if we can still count with some energy dissipation. And so it's a little bit to give us some guidance progressively, or a little bit of a contribution, a stone, without taking our stone to come up to some better understanding of how it works. But at least it's something different, it's something new, it's research. And I mean, I basically have been finding it quite fun to understand a little bit more about it.
Thank you. Okay, so we have two raised hands. First, Professor Berzer. She was the first one, and she's a lady. So, Professor, please.
I'm not sure I can use camera as well. Thank you. First of all, thank you very much for a very interesting presentation. I really enjoyed all the topics that you covered. Let me go backwards. I mean, first from the last one, I did some research in the past on it was beams reinforced with GFRP many years ago in Canada, and Canada has a history of doing design manuals, standards, and all that. I mean, irrespective of that, I feel that certainly you cannot expect too much ductility or no ductility at all, so you can increase strength in any structure that uses these bars. But I'm wondering, since you have shown some interesting research with some dissipation devices, that if you combine these GFRP bars with some form of dissipation that is happening outside the GFRP, that might be a solution for higher seismicity zones. Otherwise, if you are just looking for elastic or strength of the structure, then that they work very nicely. And I like your tests on the bond length or bond. It's also actually really challenging and interesting topic. So it's interesting. It's just a comment on that, in fact. And another question I have is from the beginning of your research on the out of plane instability walls. I again have experience on doing this research on reinforced masonry shear walls with one of my students at University of British Columbia in the past. And I was following what you and Katrin Byers, of course, group did at that time. So it's very important research, and I'm wondering in terms of the practical recommendations out of, or even I know there were some models published later on and to prediction models, but based on your tests, did you mention, I think, today at least, the effect of the axial load level on the walls on the on the onset of out-of-plane instability. Did you find that that matters? So you talked about reinforcement ratio and other factors, and of course thickness. But did you vary it? I don't remember, or did you use, because we did not get the chance to have a higher axial. We had very low axial load, axial compression, and we had a trouble inducing the instability in the reinforced masonry walls. But it's a different material, actually, technology, reinforced masonry, reinforced concrete. So that may be the reason. So any comments on that, and also on practical aspects of this research?
No. So thank you, Svetlana, if I may call you for your first
Svetlana,
name.
yes, that's right.
I know that you also had already given a presentation here, like one of, I don't know if you one of the last, and very, very good questions. So you are first, regarding your first comments on, I mean, that is actually the idea behind is that in the future, eventually we'll be able to combine some, say, larger dissipation or more ductile materials with GFRP, so locally in the plastic hinge region, be it steel or be it some of the other, for instance, the shape memory alloys. And so this is, but you know, everything has to come like one step after the other, and there is so little information even on just walls to see what is the stiffness, what is so there is still some preliminary steps to be done, but that's absolutely a very, very good comment. Regarding the effects of the compression force on the out-of-plane instability, to be very honest, I have not been working directly on this topic for now several years. We didn't vary this. This was not a parameter that we could vary in our experimental test. We did do some parametric analysis. I remember with Angelica in using finite element analysis with Diana, where we varied the compression loads. Now, I can't remember all the details. My impression is that, of course, the higher the compression load, the easier it would, the out-of-plane instability would take place. Mm-hmm. But I also have the impression that it was not, let's say, within the possible, let's say, within the range of axial load ratios that one will have for walls. If I remember well, it was not a major effect. But I would have to come back to this. So this is what I can tell you from memory, but I maybe not give you 100% of...
Because I think it does, but you did have in your experiments, you did have a level of, you had axial compression. That's what.
Yes. We had. I think it was 5%. Okay. Yes, we had. Yes.
You had 5% of the total. What was
it? Of the axial load ratio, I think so. Yeah. Yes.
Okay.
That's so it clearly affects. But then there is also a range of axial load ratio that one can have. Say for a medium, like 5-10 story building, does not change dramatically. So. So very good questions.
Thank you. Sorry, I didn't introduce myself. Thank you very much, João. And
I know you so.
Okay,
thank you so for your interest.
There are more questions. Yes, thank you.
Thank you. So Professor Stojadinovic is the next one.
Yeah, thank you, Vladimir. I wanted to ask something else. I mean, something maybe more down to earth. First of all, the thickness of the walls appeared as a problem in Chile in 2010 or so, and then in response, first the Americans and then many followed with a limit on the thickness of the walls, which is about 25 centimeters, if not more, depending on the situation, but about 25. Do you think that thickness is effective, that thickness requirement, minimum thickness requirement is effective, and in doing that, or should it have been somehow proportioned with respect to the height of the wall, total or story height?
Mm-hmm. Yes. So, I mean, again, I believe that this topic of the global out-of-plane instability is, this is my opinion, it is given too much of a research effort with respect to many of our unknowns that you have in so many other fields. So, the global out-of-plane instability, if we have again, like something like for instance, like again, the different codes will give different values of this minimum thickness. For instance, even the Euro code, there is always like you have to take the maximum of depending of whether it's the web or where is the flange, and it goes between 15 centimeters minimum to 25. But I believe that the 25 millimeter, which in practice is what we need, the minimum that you have if you want to have 2 layers of reinforcement. I don't think that the global out of plane will be buckling will be something that will be at risk. And actually, even from some of the results, some of the post reconnaissance or the reconnaissance missions in earthquake affected areas, where we could see members that seem to have failed due to somehow of a sort of a more or less global out of plane instability. Actually, they could have been also triggered or have contributed by other modes, like out of plane displacements that could have been excessive and that should not have been that excessive if the building had been properly designed. So I think there is too much I don't think it's too much of an issue, the global out of plane instability. Something different is the more local forms of instability that we often see, typically connected to also to some incipient rebar buckling that can extend sometimes over several stirrups. And so this is something that proportionally I would place more research focus on this more local out of plane instability than a global out of plane instability. I don't think that this is something that we will see a lot in again, except if we are really dealing with very small thicknesses as they are doing in Colombia, in some other countries with 8 or 10 centimeters and with 1 layer of reinforcement. There clearly it can be a problem, especially also because they often combine it with very low ductility steel. So yeah, so sorry for the long winding explanation. This is a little bit my view.
Yeah, I mean this I agree with. I mean, yeah, it's a long explanation, but it is important to remember that in practice, a solid, healthy thickness of the wall does a lot of good.
Of course.
Yeah, and then the next one is with torsion. I mean, your interaction diagrams show that there is a very significant decrease of the moment capacity of the wall, which we would consider its primary resistant capacity when the torsion moment exceeds a value, the value when the line becomes straight. And that's, I don't know, a little bit more than half of the torsion capacity of the wall. Well, okay, determining that 0.6 of the torsion capacity is good and nice to know, but is there a way for a designer to use other measures in terms of giving the structure more symmetry, giving the structure a way to control the amount of torsion by reducing eccentricity and therefore preserve the moment capacity of the walls? Would that be an incentive to change the structural configuration rather than fight torsion somehow?
Yeah. Ryan, do you want to maybe address this question?
I mean, I agree. I think you're on the money with both of those things. I think, first of all, I think increasing the wall thickness, in my view, is just the easiest thing to do to avoid out of plane instabilities. And I think it's the same approach for a building, right? Like, you want to avoid torsion as much as possible by making sure that there really is. I mean, it's difficult to avoid, obviously, because engineers are obviously fighting architects as well in terms of where you're placing these walls. So you're always going to have some, let's say, eccentricity of the center of stiffness away from the center of mass. But, certainly trying to avoid the example that I gave where you have that building core right out on the perimeter. I think it's common practice now to do that, but I certainly know of a lot of buildings, for example, where I'm from in Australia, and in a lot of other regions of low to moderate seismic regions, where you have one core that's basically resisting everything, and it's placed out on the perimeter, which I think is madness. But these buildings were designed before an earthquake actions code was even available. So yeah, I think it's simple things like that. But of course, in some cases, it will be unavoidable, and in that case, you will need some sort of design approach to estimate the effect of torsion and how it plays into the bending moment capacity. I don't know if that's completely answered the question or.
No, I think that's where I was going. And then the other thing that I also want to point to everybody is that the warping torsion is an important element in the calculation and the warping moment of inertia, the torsional resistance due to the characteristic value of the torsional resistance that I omega. And,
yes.
and very, very good sections that have a lot of I omega are boxes, and perhaps even
yes.
a partial box where the vertical utilities could be placed behind around this elevator core or the stairway core would help increase somehow this I omega. And that may also give some leverage to designers who cannot completely convince the architect that everything should be in corners and only one corner. They could start adding a box somewhere there and maximize their I omega with whatever they have left. So
yeah.
these are nice ways to look at a building, not only in terms of elements, but also in terms of systems.
Yeah, I think as well, something that I certainly want to look to in the future is not just having a U-shaped section, but what if you actually have the coupling of the coupling beams, or even just the slabs, and how much of a role does that play in terms of restraining the warping? And then you have maybe more circulatory torsion contributing to that, and that in effect will, I think, increase the torsional capacity in itself. So
yeah. So there are ways to play for sure.
Sure. Yep.
Okay, let me leave the floor. Obviously, we can talk for a while, but it's if somebody else has a question.
More questions? I think this was the longest discussion that we ever had, and I'm happy about it. Thank you all. So if there's no more questions, I can once again express my gratitude to João and Ryan. We enjoyed the presentation, which the discussion is the proof that it was pretty challenging for all of us. So I hope to host you sometime in the future again, and I wish you all the best.
Thank you very much.
Thanks again, Vladimir,
Boza.
It was our pleasure. Thanks to everybody. I hope it was useful in a way.
And if anyone is interested in any of the references that we put up, just shoot us through an email, and we'd be happy to share any of the publications and stuff.
Perfect.
Thank you.
Okay, thank you very much.
I'm going to switch to Serbia now. Thank you.
Okay.
Bye. Hvala svima na prisustvu u prezentaciji. Nadam se da ste uživali i vidimo se nekom sledećem prilikom. Prijatan dan.